Alright, we're going to talk about related rates, which if we're looking at numbering this is lesson 2.6. Before I get into the bulk of our lesson, the point of us doing these related rate deals we're going to be using finding derivatives for this over time. Think of a tank of water that's shaped like a cone. What this related rates idea explains is how the volume, the height, even just the radius of the circle in that cone changes as the water drains over time. So let's just get right into it. We're going to look at our first example even right away. We're going to have the variables x and y are both differentiable functions of t and are related by the equation y equals x squared plus 3. We need to find dy dt. So we need to find the derivative of y with respect to t when x is equal to 1, given that the derivative of x with respect to t is equal to 2 when x is equal to 1. So what we're going to do in this is we're going to start by just writing that equation we were given. Y equals x squared plus 3. And then what we're going to do is we're going to, on both sides, write d dt, finding the derivative with respect to t of y, is equal to d dt of the expression x squared plus 3. So on the left side, we're just going to replace this with, instead of d dt times y, rewrite it as dy dt, which is totally fine to do. And on the right side, what we're going to do is we're going to, well, in fact, using the chain rule, we're also taking the derivative of y, which is just going to be 1. Then we're going to take the derivative of our other side of the equation. 2x would be the derivative of x squared plus 3. And then we're going to write dx dt. Now, we know from the problem that dx dt is 2 when x is equal to 1. So we're going to replace x with 1 and dx dt with 2 so we can find the value of dy dt. So dy dt is going to equal 2 times 1 times 2, which is going to just equal 4. And that's the answer we're looking for. Now this wasn't really a whole application of related rates. It was just kind of looking at it generally. So let's look at one more example. And this one is going to be more of an application. So example 2, we have a pebble is dropped into a calm pond, causing a ripple or causing ripples in the form of a concentric circles. not of aconcentric circles, of just concentric circles. So I'm going to get rid of A. The radius, r, of the outer ripple is increasing at a constant rate of 1 foot per second. When the radius is 4 feet, we need to know at what rate is the total area A of the disturbed water changing. So there's a few things we're going to write down while setting this up. We need to know, one, this problem is talking about area of circles. So we need an equation. And that equation is going to be the formula for the area of a circle. And if you think back to what you learned in geometry, the formula for the area of a circle is A equals pi r squared. Now we're also going to write down the given rates that we know. We know that dr dt, the change of the radius over time, is 1 foot per second. And we know that we need to find the change of the area. So we'll write that as dA dt. We need to find that when r equals 4 feet. When the radius is 4 feet. So let's start by just writing our equation. We know we need to find the derivative of the area with respect to time. So what we're going to end up doing is writing dA dt. So we're taking the derivative of each side with respect to time. Derivative of A will just be dA dt. When we take the derivative of pi r squared, we're going to get 2 pi r dr dt. Now we know dr dt is 1, and we have an r value of 4. So let's replace 4 and dr dt. 4 for r and 1 for dr dt. So dA dt is going to equal 2 pi times 4 times 1. Well, let's go. 2 times 4 times 1, that's 8 pi feet squared, because this is area, per second. That means the area of that circle caused by the pebble dropping into the pond changes at a rate of 8 pi square feet per second. And that is exactly what they asked us to find. Now, I'm going to give you some general guidelines quick on what you would need to do when doing this related rate stuff. So the first thing we need to do is identify all given quantities and quantities to be determined. And then, if we can make a sketch and label the quantities. I didn't do that in the last example, but I have more of an idea of what circles, like a rippled pond effect, looks like. The second thing we would do is we need to write an equation involving the variables whose rates of change either are given or are to be determined. Then we can use the chain rule to implicitly differentiate both sides of the equation with respect to time t. Finally, after completing step 3, we can substitute into the resulting equation all known values and values for the variables and their rates of change. Then solve for the required rate of change. So, before we move into another example, I want to give you a little bit of a table that has a verbal statement and a potential mathematical model that can represent that statement. So, first I'm going to make a list of just the verbal statements. So we'll write a verbal statement, and then we'll go a little over to write mathematical model. Now, verbal statements. The first one is going to be the velocity of a car after traveling for 1 hour is 50 miles per hour. Then I'm going to give us a little space to write the mathematical model in a second. Another verbal statement might be something like water is being pumped into a swimming pool at a rate of 10 cubic meters per hour. Another verbal statement could be a gear is revolving at a rate of 25 revolutions per minute, where 1 revolution is equal to 2 pi radians. And then lastly, we'll also write a population of bacteria is increasing at a rate of 2,000 per hour. Now, if I were writing a mathematical model for that, it might look something like this. For the first one, I might say x is the distance traveled and I might say dx dt the change of x over time is 50 miles per hour when t is 1. For the second verbal model, we might have a model looking like V equals the volume of the water in the pool. And dV dt is 10 cubic meters per hour. For our third verbal model, a mathematical model might look something like theta is the angle of revolution and d theta dt is 25 times 2 pi radians per minute. And then this last verbal model we might represent as x equals the number in population and dx dt is 2,000 bacteria per hour. So I'm looking at the time we've got in this video. I think we'll move into our next example. In fact, our next 3 examples we can probably get covered in our next video.